Good morning, everyone. I hope you guys are having an excellent day. We're going to continue with our gas law discussion. We're just finishing up right here at the end of section 5.6. I ran out a little bit of time. I want to make sure I keep these somewhat a little bit shorter and don't get too long-winded. So we are talking about the relative speed, velocity of a gas molecule. And if you take a look at this, you can see that the number of oxygen molecules at a given velocity. So this is going to be our optimum spot. And if you were to draw, it's not very straight, but if you were to draw two lines going down, this is where you would have the highest probability of finding the velocity of those certain oxygen atoms or molecules. Now, they don't all have this velocity because of the number of collisions and the temperature and the situation that they are under. Now, if I take and plot nitrogen gas at three different temperatures, you can see their different velocities. So it should make sense to you that as I increase the temperature, okay, the range of the velocities also increase. So you can see that here the range is much narrower than when I have a very high temperature gas. So the peak represents again the most probable velocity, and that the increase in velocity is going to happen as I increase the temperature. So now we're going to talk about effusion and diffusion. This is something that you guys seems logical. You've talked about this before. Just put it in chemical terms here. So diffusion is the rate at which gases mix. Gases, we are talking again about gases. We could talk about liquids. You can probably imagine mixing liquids, but they don't behave as nicely. There's more interference there. So we're going to stick with gases. Diffusion is the passage of a gas through a tiny opening into an evacuated chamber. And both of these things, if you can think about it, that if you are smelling a pungent odor or if you spray some sort of perfume or something like that, it takes time for the odor to disperse throughout the room. That's the kind of picture you should have right now as to what's going on. Measure the speed at which a gas transfers into a chamber. All right, so here's our little chamber that we have here. And you can see that we have a vacuum on one side. Again, we have these gases. Remember, they're constantly moving at very high velocities. They are colliding with the wall. They are colliding with each other, and they're creating a pressure inside of here. Now, through that movement, obviously some of the gases are going to want to go through this pinhole. And how fast is it going to be able to make its way through there? So this is our formula that we're going to use for that. So you guys can see that we have Graham's law of effusion. The rate of effusion of gas 1 over the rate of effusion of gas 2 is equal to the square root of their mass. And again, because that's a capital M, that is going to be the mass of a mole in kilograms. So mass of a mole in, you don't need that, in kilograms. Okay, so M is molar mass like we just said, but it has to be in kilograms. All right, so if we take a look, this law of effusion, it has to do with distance. If you can imagine, obviously these gases are colliding, they are also traveling. So the distance traveled by gas 1, distance traveled by gas 2, you can imagine that that's going to be affected by the mass of each gas. So if we assume something like a gas chamber, just a very simple one, and we have this pinhole going through here, and our gas is going to come through here. And one of my gases that I have is methane gas, which is a gas that we have in our gas jets. And the other one that I'm using an example of is chlorine gas. Well, of course they're going to collide. There's not any intermolecular attractions between these two, so they're just going to continue to collide. And they're going to make their way through our gas chamber here. Well, if I take the distance traveled by gas 1 and the distance traveled by gas 2, so I am going to be taking the molar mass. So the molar mass of chlorine is 70, chlorine gas is 71. The molar mass of methane is, is 16. All right, so as we can see that this rate is going to be a fraction between a factor of each other. I take that and divide that out, and then I'm going to take the square root of the number. Sorry, I don't have this calculated out. So it's 2.1. So what this means is that the rate at which these are going to go through, that the methane is going to go through 2 times faster. So a direct relationship between those two. All right, so again, this is what you would see if we had it in a gas chamber, that you would be able to see it. So we have ammonia and we have hydrochloric acid that's vaporizing. And if they're going to move each other to each other, you're going to have one moving in this direction, you're going to have one moving in this direction. Imagine that we released them from these ends. They're going to meet somewhere in the middle, and that's what you're going to see. Now, these gases are both going to be moving at different velocities. So if you want them to reach a certain point at a certain case in time, you're going to have to factor in that distance that they have to travel and the speed at which they are going to be traveling at. Again, they are doing all sorts of collisions along the way. So we've been talking all along about ideal gases. Now we're going to talk about real gases, which are very, very difficult to study. Thank goodness we don't have to do that. It says no gas exactly follows ideal gas law except if it's going to be at low pressures and high temperatures. Very important to remember. Low pressure and high temperatures. At this time, we can assume that if we're at low pressure and high temperatures, that we'd have virtually no interactions between the gases. And then that's helping us to analyze them as an ideal gas. Well, what happens when we don't have that? So you can see, let's see if I have, oh, I must have an empty page in there. Okay, so if I take a look at this, I have plots of PV equals nRT of pressure. You can see I'm in atmospheres of several gases. So this dotted line is an ideal gas. We're at 1 atmosphere, right, which is at STP. And you can see that as I increase my pressure, that the gases continue to deviate. So here is low pressure. Here's high pressure, deviating far away from the ideal gas law. What happens when I do the same thing and I take into account the pressures? Again, I'm at low pressure. Look how well these gases behave. The minute I start taking a look at increasing the pressure and the temperature is involved, it's not as ideal. So which one is the most ideal? You can see that one deviates the least. So we have low pressures and high temperatures. Those are the best scenarios or parameters that we could set up in which gases would behave ideally. Well, do we need to modify this kinetic molecular theory to fit the behavior of real gases? Like, what if we want to really study this? Well, it becomes very, very complicated. Johannes van der Waal, you're going to talk about van der Waal's forces in a couple of chapters. He was the first person to do work in this area. He was a physics professor. You'll see these complicated equations in just a second. He received a Nobel Prize in 1910. So way back then, they were trying to take a look at how can we really study gases. So we can take the actual volume of the container. We got to subtract out the moles of the gas and the empirical constant from the equation, because every gas is going to act differently depending upon its makeup. Well, if we continue to allow for the attractions that occur that we do know are happening, but for the ideal gas law, we negate those. We say that they're zero. So the pressure observed is going to equal to our initial pressure that we think it's going to be minus this correction factor. The correction factor depends on the concentration, because the amount of interaction is going to depend on the concentration. I didn't say this is going to be easy. There's a lot of correction factors that have to go on here. Thankfully, we aren't going to do much with these. This is the only thing that we really, really need to take a look at. And gas at low concentrations, relatively few interactions. That should make sense to you. Here I have a wall. Yes, there's going to be interactions with the wall. Collisions with the wall. And there's going to be few interactions between these molecules because there's not very much of them. But remember that they are moving very quickly. They're colliding independent of each other. Energy is conserved. All of those things are still happening. But look what happens when I add more molecules. There's going to be more interactions, there's going to be more attractions or repulsions. There's also that with the wall. And so then in this case, the pressure is going to drop some. So this one right here is going to act more like PV equals nRT than the one on the right. And that is because we know that there's more interactions, there's going to be lower pressure on the wall, there's not going to be as many collisions over here because they're too busy interacting with each other. Where over here, they'll collide some, there'll be some interactions, but they'll hit the wall and they'll keep on going. So this side is going to act more like the ideal gas law. And they can go ahead and figure this all out if you're given a certain particle and how many interactions would happen with all of these and all the different combinations. And so now we're talking about how much volume there is and how much the attractive force is. So in here, you could have 45 pairs of collisions, and we're only talking about 10 particles. Well, that's nothing compared to the gas that's around us. So it becomes very, very difficult to study real gases. Now take a look at this. This is Van der Waals equation. This is what, if we were going to study gases in the real world, real gases, this is our formula. I don't know about you, but I really don't want to deal with all of this. But we just want you to see that there is a correction factor there, and this corrects the flaws in the kinetic molecular theory. So the corrections explains real gases behavior, provides confidence to understand the fundamentals of gas behavior. Good, important chemistry takes place in the gas phase. Great, gas phase. That's about all that we need to remember. Here it is again, and you can see PV equals nRT. So we are going to stick to this simple problem because it's a lot easier to understand. I don't think this is anything that we need to really worry about. So we are done with Chapter 5. Excellent work. Make sure you keep working on your problems. See you in class.